All right, so welcome everyone to this week's coaching seminar. It's my pleasure to introduce Daniel Hoffmann, and he will speak about fields with derivations and action of finite group.
So first of all, thank you for inviting me and allowing me to speak here at the seminar. You know, when I was a PhD student, I remember that I had this kind of, wish that I will at some day speak at the seminar. So yeah, that's a great moment for me right now. And today I want to give you this mild introduction to the algebraic model theory or model theoretic algebra, depends on the perspective, and then give you one example of actually a quite new theory, a theory where you have differential structure and differential structure at the same time. And this theory is an example. I mean, this is an example which comes from my joint work with Omar Leon Sanchez, and I guess he's in the audience. So I have possibility to make, some writing here. So when you have a question, you can just ask, and I will try to provide you more details. Okay, so let me start. I prepared this draw, and I did this like just a picture made by hand because I had some problems this week with my MikTeX. So my computer didn't, there was some issue with the tech. And finally, I just decided to do it by hand. Okay, so here's the, in model theory, usually we just are interested in fields, okay, in theories of fields. And there are modules, there are vector spaces, also some rings, theories of rings and other stuff. But in this core of neo-stability, I think that fields play the crucial role. So here in this picture, we have 4 different kinds of fields. Fields, pure fields, that's the first part here. That's just fields without, so fields in the language of rings, okay? And then you have differential fields here and difference fields, so fields with some automorphisms. Okay, and fields, pure fields are, the main examples are algebraically closed fields of characteristic 0 and p. Then you have separably closed fields of characteristic p and Yershov degree e. So it means that it has such a field has a p basis with e many elements. Then you have pseudo-finite fields, PAC and Frobenius. Frobenius fields are just a subclass of PAC fields. I will speak today a little bit about PAC fields. And then you have large fields. And that's quite, okay, the large fields were introduced by Florian Pope, but they get more attention recently due to the so-called étale topology. And then in differential case, you have DCF0, DCFP, which are quite obvious, differentially closed fields of characteristic 0. Then you have Hasse-Schmidt. Okay, I will make a link here between Hasse-Schmidt and separably closed fields, because actually separably closed fields and fields with Hasse-Schmidt derivations are bi-interpretable. So that's actually the same theory, but in different setup. Then you have PAC differential or packed differential and large differential. And they also are quite new or recently studied. On the other hand, you have difference fields. So ACFA, it's a field with one automorphism, actually existentially closed field with one automorphism. Then you have QACFA, QACFA, and that's field with existentially closed field with automorphism, which correspond to Q, right, rationals. And then you have Gtcf. So because Gtcf it's a model companion of the theory of fields with group action of a given group G. Okay, so we fix a group G. I will tell you more details about this later on. So we fix a group G on and its action on a field by automorphisms. And if it has a model companion, we call it Gtcf. So G transformally closed fields. Okay, so we needed to use T because you cannot have that everything is GDCF, right? I mean, differential difference. That's something which makes some problems sometimes with inventing these names. Okay, then you have SCFA, which is separably closed fields with automorphism. So actually it's a field with a distinguished P basis and one automorphism which fixes this P basis, which preserves the P basis. And then there is a generalization where you have also fields with a fixed P basis and group action by automorphisms of group G, which also fixes this distinguished P basis. Okay, so that's the setup above. I mean, there's these three categories, and there is this last one at the bottom here. So when you have both structures, both types of structures at the same time, so difference, differential, and they were also studied already. So you have DCFA, which is fields with derivation and automorphism, differential automorphism, existentially closed fields. And then DCFA-MN, so almost the same thing, but you have M many derivations which commute, and N many automorphisms which are differential automorphisms, and they also commute. Or no, they don't. No, they don't. And today, at the end, I will talk about this last example. So it's a theory of fields where you have a characteristic 0, M many the derivations which commute, and group action by a group G, which is group action by differential automorphisms. Okay, so if I will take out large fields from this picture here and here, every field which is a model of these theories is a PAC field. Just to make it make this statement. So if I think that the PAC or PAC fields are quite important, and the techniques from PAC fields they will show up later or earlier or later on. If you try to do model theory of fields, you just face PAC fields. Okay, and I made these colors, so green or blue, I think it's green. The green states for stable theories. So you can see that if you start with pure fields and then add derivations, usually you are still stable field. I will provide a definition of stable field in a moment. And also of, of stable theory and also of simple theory. Simple is just one step from stability. So if you start with a stable field like with these guys and add derivation, usually you are still a stable field. Okay, so that's like something which is like some kind of behavior which is there. On the other hand, if you start with a field which is stable and try to add an automorphism or many automorphisms, usually you are not stable anymore, but you are just a simple field. Okay, any questions? Are you there?
Yes.
Yeah. Okay. It's. I don't see your faces, so I don't know. Okay. Let me go on. So there is this important question. Okay, because I'm showing you all these examples of model companions, right? Of classes of existentially closed fields with some operators. So that's a natural question. Why do we produce all these model companions? Okay, so theories of existentially closed fields with operators. And there are two, I think that there are more answers to these questions, but there are two which I experienced or somebody answered in this way to me. So the first approach is like string theory approach. You know, the string theory in physics is like they developing a lot of theoretical stuff, and they have no technology to make the experiment and check the predictions, right? I mean, you need to have like a linear particle accelerator of the size of the solar system. I mean, no. So why it's similar to string theory, I mean, producing all these model companions, because one of them, I mean, some of them were used in outside of model theory. So for example, Hrushevsky used DCF, right? Fields with stable fields with derivations to prove this model rank conjecture. So maybe other day there will be one other guy who will try to attack a serious conjecture outside of model theory, and they will need a tool. So he will just you know, reach for the toolbox, pick up the right range, and do the proof. Actually, I don't like this answer, so there is another answer which I like more, and that's neo-stability. So we are trying to, you know, to do all these dividing lines in model theory, and doing these dividing lines, we need more and more examples because things are getting more difficult. Okay, so the intuitions which we already had previous situations, they don't work anymore. And I draw this classical map. It's called map of universe. If you don't know, you can just go for forkinganddividing.com. It's a website done by Gabriel Ponant, and it's quite nice. And it shows how the model theory sees the universe. So here you have NIP, that's NIP, right? And here you have NSOP, okay, NSOP. I will give a precise definition which we need in a moment. And here we have at the intersection stable. Okay. So anytime when you try to do some algebra or model theoretical algebra or algebraic model theory, you will finish in NSOP. Okay, so NIP, that's a more analytic part. And I mean, people who try to do algebra or model theoretical algebra, algebraic model theory, we are here. So somewhere in an NSOP1 context, we have examples of stable fields or stable fields with operators, simple fields of operators, and right now also NSOP fields with operators. So before definitions, let me give you some intuition. What is changing? Okay, so in NSOP, and that's this the bottom half of the picture, this algebraic part. If you go with this direction, okay, so you are less and less tame, you are more and more wild. So what is changing? There we have three different examples, and in the case of stable theories, you have infinite set, right? And then this infinite set corresponds to random graph, okay? So you can take a structure which is similar but not so tame, and that will be random graph. And then if you will go one step further, there will be generic binary function. So I don't like this, okay, maybe not that I don't like this line, but it's not so important for us right now. More important are the second two lines, so ACF and vector space. So if you start with stable theory, the classical example is just algebraically closed fields, so ACF. And the quite close but not stable theory is theory of bounded PAC fields. So PAC fields which absolute Galois group is, say, finite generated. Okay, bounded, it's something more general, but finite generated implies bounded. And then one step further, you have omega-free PAC fields. So PAC field where the absolute Galois group is a free profinite group on omega many generators. And the last line is when you start with a vector space that's stable, but vector space with a bilinear form over a finite field that will be simple, not stable. And if you take a vector space with bilinear form, but over an infinite field which satisfies axioms of ACF, that will be NSOP1. Okay, I'm putting you NSOP1. That's a part of NSOP, so not so important here. The important thing which you can see in this table, in this thing is like, if you start with a stable theory, then simple theory are more random, so you have some randomness here. And then if you go further, then you have random plus independent, okay, some kind of independence. Okay, what do I mean by this? So look at the last example with the vector space. So you have a vector space, that's a stable thing. Then you have a bilinear vector space with a bilinear form over a finite field. So this finite field, you can still define it inside V, so it's not so independent. And in this last case, you actually need a separate sort for this field F to make it work. So F and V, the vectors and the scalars, they are independent. They live on an independent parts of the structure. And there is also some kind of randomness, I told you. So in all these examples, I mean, say in the second example here, actually, if you have a bounded PAC field, the absolute Galois group, it interprets a random graph. So you have already randomness there. Okay, so just keep in mind, you have stable theories, then you make it random. So, I mean, you allow some randomness, you have simple theories. If you allow randomness and also some kind of independency, then you have Nsop, in particular Nsop1. Okay, so let me start with basic notions. And if L is a language, okay, we start with a language L. For example, it can be the language of fields with derivation, so rings actually with derivation, plus, minus, dot, and 0, 1, and the derivation. And say that we have a theory, L theory T. Usually we assume that it has quantified elimination of imaginaries, that's for model theorists. And let us pick some big model of this theory. So some M, which is a big model. Then a formula phi in variables x and y has the order property. If you can find a sequence of AIs and BIs in M, such that this formula defines order, so it means that phi AI and BJ, if and only if I is smaller than J. Okay, such formulas are nasty. They will produce a lot of types, and they will make your theory quite complicated. So we want to avoid this kind of formulas. So we call a theory stable if there is no formula with order property. So you cannot define order with a given one formula, and that's stability. And I told you that that algebraic model theory takes place in Nsop, so we need to know what is strict order property. So a formula has the strict order property if you have one sequence and such that it defines this kind of inclusion, okay? This thing is the part of the model, all the tuples from the model, which satisfy formula phi x AI. Okay, so actually, and here you have a proper inclusion. Okay, so you have this formula phi and a sequence of parameters AI. If you plug these parameters, then the set defined by this formula gets bigger and bigger and bigger. And in some sense, okay, it also defines an order, right? This formula defines order in a stronger sense. So in Nsop, here's Nsop, if there is no L formula with this strict order property. Okay, so you allow some formulas which define order property, but you don't allow formulas which have this strict order property. So in Nsop, you are able to define order, but it's a little bit harder than outside of Nsop. And still, this Nsop, again, the part of model theory where the classical algebra happens is quite big and diverse. So we decided to divide it further. And let me just, before I will go to the less general stuff, let me just point out come back to this question, okay, why do we need all these model companions? I told you we need a new source of examples for model theory. And that's exactly why, because I think that we are quite far from understanding even this NSOP1 environment. So if you have a stable theory, in a stable theory, you have this forking independence. So there is a notion of independence. In most of the theories with fields, it's just linear disjointness or algebraic independence. And people notice that this more general model theoretic notion of forking independence, if it satisfies some axioms like symmetry, then the theory is still quite nice, and they call it simple. So simple theories, they were developed using axiomatic approach to some abstract notion of independence. Okay, then there is another way of describing simple theory. It's a theory where you don't have if you have a formula, you cannot have this tree property for a formula. I will skip this. It's not so important right now. I'm just saying that there are two options for defining all the subclasses of NSOP. So the first one is you just try to have a nice notion of independence. Okay, that's an axiomatic approach. The other approach is a combinatorial one. So you want to avoid, I mean, previously we want to avoid formulas which define order. Now we want to avoid formulas which define something more sophisticated, and it's called tree. Okay, we want to avoid formulas with tree properties, and that's actually the NSOP hierarchy. So you want to avoid some kind of tree decomposition of your formula. And NSOP1 is somehow special because it joins both, like simple theories, like simple. It joins both of these approaches at once. I mean, you can define NSOP1 by this axiomatic approach to some abstract independence relation, or you can say that there is no formula with some kind of tree property. However, the higher NSOPs, this hierarchy here, there is no good notion of independence there. Okay, maybe in an NSOP3 you have this free amalgamation, but that's some minor thing. And we are at this moment where our axiomatic approach works, but it's quite difficult, and it works only to some level. And if you want to go beyond it, then there are some problems. Also, in the case of NSOP1, if you remember, there was this example of vector space with a bilinear form over a field which is algebraically closed. So this theory has a nice natural notion of independence, which is better and works better than the model theoretic notion of independence from this picture. So we are at the situation where there are some things in particular examples, there are mathematical objects in particular examples, which work better than the objects coming out from model theory. So I think that we are far from understanding what is the right notion of these dividing lines. And then therefore we need more examples. Okay, so do you have questions up to now? Are there any questions?
I think you're okay. Good.
Okay, so now I will tell you, right, how to produce these examples. Okay, so because we want to have examples to make this thing, to understand this, dividing lines in model theory. So we want to start here. Okay, we want to take a stable theory and then have an algorithm which will, moves our theory. It will make it worse. Okay, it will break stability, but we want to do it in a controlled manner. And there are two ingredients to do it in a controlled manner. And the first one is pack ingredient. I will call it pack ingredient. And the second one is group action. So why pack ingredient? Pack ingredient is to make a use of Galois groups. Okay, so we have absolute Galois groups, and we know for that for at least for pack fields, PAC fields. I'm sorry, I'm just messing. Sometimes I'm calling them PAC, sometimes pack. So PAC fields, they are controlled by the Galois group. I will tell you about that in a second. And group action is to break stability. Okay, so in the first slide, I told you that if you add automorphism and get different structure, then usually you are not stable anymore. And also group action, a proper group action will shape Galois groups. So let us start with this pack ingredient. And pack ingredient, okay, so we know, I think that we know what are existentially closed structural fields, or they are just the structures which, if you have overstructure and there is a solution to some equation or formula, there also exists in your initial, the guy which you started the situation, right? If you have, say, K and F and K is existential, okay, if you have K, which say a field K is existentially closed, every time when you have a overfit F and a solution to equations in F, there exists a solution to equations in F, so there also exists a solution to these equations in K. And that's, if you think about that, that's just exactly ACF, algebraically closed fields. So if you take a existentially closed fields, then you just get algebraically closed fields. And okay, so they are quite special, and they imply that you are PAC field or PAC structure, and that implies a large field. Okay, so this first line actually, it's well known in the case of fields. Existentially closed fields are PAC, PAC fields are large. And let me give you a definition. So PAC field is existentially closed field in all regular extensions. Okay, algebraically closed field is existentially closed in all extensions. And here we are just interested in regular extensions. What is a regular extension? It's a separable extension which is, the smaller guy is relatively algebraically closed in the bigger guy. And that's it's the same as saying that every absolutely reducible variety has a point in K if you're saying that K is a PAC field. And using this, you can define what is a PAC structure. So you are just existentially closed in all regular extensions, but here it's a regular extension in model theory. So you actually take the algebraic closure operator in this model theoretic setup. So you are relatively algebraically closed with respect to the model theoretic algebraic closure. So for example, if you are like differential field, then say K in F is regular. So you have two differential fields K and F. So K and F is regular if intersection of F with the algebraic model theoretic algebraic closure of K is again K. And that's equivalent to this more model theoretic definition that each stationary type is finitely satisfied. Okay, and this thing is just to tell you how you translate varieties to the types, and that's it. Okay, so if you have a model of a theory, right, say M is a model in T, then you can take a subset in M, and you can consider so-called absolute Galois group. So absolute Galois group is just the automorphisms with respect to your language L of algebraic closure of the model theoretic algebraic closure of A, which fix A pointwise.
So do you assume here that T is PAC or something like that?
I'm not assuming right now any PAC. Okay, I'm just taking any theory T. Okay, I would like to assume that T is a stable theory. That's stable. I hope that I wrote this. Okay, I didn't, so I should. So I'm assuming that T is stable, and that's it. And now there is a theorem. Okay, T is stable. And the theorem tells you here. So K1 and K2, you take a substructures in some model, say monster model of T. Okay, they are just substructures, but they satisfy this condition that they are existentially closed in all regular extension inside this monster model M. So you take another substructure, another structure which is embedded in M, and then which is regular over K1, and then you expect that all the existential formulas and also have solutions in K1. Okay, so if you have two such structures, substructures of M, which are PAC substructures of some sort, there is stable M, and say that they contain a common definably closed substructure F, and this diagram holds. So K1 and K2, they have isomorphic absolute Galois groups over GF, and here you have just restrictions, right? Then what's important, K1 and the K2, they have the elementary equivalent over F. Okay, so let me give you an example, and I think that will be a good moment for a break. So here we have an example in the differential context. So say that you have let T be DCF0. Okay, so you have T which is DCF0. Then you take a monster model. I think that sometimes people call it universal domain. And we are now interested in all differential subfields of this monster model. Some of them can be elementary substructures, so models of DCF0 on their own, but some of them may be just differential subfields, okay? But we are interested in all differential subfields. And we see that K in L is regular if and only if L intersected with algebraic closure, the differential algebraic closure of K is K. So because K is a differential subfield, you can actually write here just the usual standard algebraic closure of K. Okay, so in other words, being regular in the sense of in DCF0, okay, as a differential subfield of a model of DCF0 is just being relatively algebraically closed. And separability comes for free because you are in characteristic 0. So let me remind what is PAC? PAC differential. So something is a PAC differential subfield, right? This guy in monster model. So a differential subfield of a monster model, if it's existentially closed in all regular extensions. So in all differential subfields of my monster model of this U, which are regular extensions of K. And let us know that PAC and PAC differential are that's not the same. You have implication from right to left. So PAC differential is something stronger than the pure field PAC. If you add the derivation, then you require a little bit more. Okay, and we know for general reason that differential absolute Galois group, so the automorphisms which preserve the differential structure actually are the same as the automorphisms which don't preserve the differential structure. Potentially don't preserve, okay? And we also know that the algebraic closure of K of a differential field is just a pure algebraic closure, the model theoretic differential ACL of K. And we also know that this holds, right? So the automorphism, differential automorphism of the algebraic closure of K is just, again, the thing here. It's the explanation of what I mean in this slide. Okay, so if you use this diagram, okay, this theorem, it will tell you the last thing. So if you have two PAC differential subfields of your monster model and they have the same algebraic symmetries, right? So the symmetries of okay, just they have the same automorphisms, pure field automorphism, say over some ACL over the differential closure of algebraic differential closure of Q. That's the this thing plays the role of F here, so this bottom part, right? And that's what I mean here. So after taking the restriction to the absolute Galois group of this Q, then they solve the same differential equations over Q. Okay, so they have the same theory, first order theory, and if in one of these PAC differential fields you can solve an equation and you have the same isomorphic absolute Galois groups, yeah, then you can solve the same equation in the other field. Okay, so I think that I can make a break here because then I will speak about group action, and then I hope that I will have still some time to give you this example. Okay? Sure. So I think that I just did too much in the slides and I prepared too much. So I think, skip some technical details at the end. But right now, let me just go with what I prepared. So I told you before the break about this first ingredient on the procedure to break stability. So the PAC ingredient. Now I will go for the second one. So group action. So let me just remind you that the output was that if you have a PAC, if your structure is PAC, then you control it by the model theory of this thing. You control it by the absolute Galois group. And existentially closed fields, existentially closed structures, they are PAC. PAC is just generalization of being existentially closed. So now group action. And again, let me just come back to this first slide. So why group action, right? We want to start with something which is stable, and then adding difference structure, we are getting things which are not stable anymore. They are usually just simple. So here I made two marks about this Gtcf 0 and Gtcf. So the simplicity or more general and properties of these two theories, they also this one here, they depend on the particular choice of the group G. So they are simple, all these three theories, this one, and this one, if G is a finite group. So let me define this group action. So you start with a theory T in the language L, and you fix a group G, L. And then you define LG as the language L extended by sigma G for each element from your group G, and sigma G that they will play a role of the automorphisms. So there a pair MG, so M with this sigmas on the second, I'm just using G to denote all this collection of sigma Gs. MG, this thing is, the structure is a model of theory TG. So you start with theory T and then you define theory TG. If M is a model of T, okay, and then this map, so taking G to sigma G, is a group homomorphism. In other words, sigma G's, they define a group action. So if you take sigma G and sigma H, it corresponds to sigma G times H. And the next step, which is less obvious and more difficult, is to find model companion of TG. Sometimes it doesn't exist. A model companion is the theory of all existentially closed models of TG. So this class might be not elementary, and model companion may not exist. But in many examples, it exists. So, for example, ACFA, right, ACFA, arises as if you take T, the theory of fields, and then for the group G, you take Z. So ACFA is a theory of fields with one automorphism, but this one automorphism corresponds to the generator of Z, of the integers. And SCFA, so separably closed fields with automorphism, that's just T, which is a separably closed fields, right? So in the language of fields with P basis, with distinguished P basis, and then again you take G being the integers. And one more, so Gtcf, and that stands for the theory of fields. So this time not, okay, so T is just theory of fields. It's not stable, right? Theory of all fields, that might be not stable. I mean, that's not stable. And then energy, okay? You can just plug energy, and sometimes this theory Gtcf exists, sometimes not. So we know actually right now at this moment, state of art says that Gtcf, so the transformally closed fields with group action of group G, exist as model companion for all virtually free groups. So a virtually free group, it's a notion which at the same time generalizes finite groups and free groups. So virtually free is free. You have a finite quotient and then you have free group, right? So it's free after finite quotient, or the other way. There is a free subgroups that it makes it that's the quotient over it. It's finite, one or another. Okay, so if you have a finitely generated group G, right? Because we need to have some connection between G and properties of model theoretic properties, and we will establish this by looking at the absolute Galois groups. So okay, so we start with G, which is finitely generated, and then say that we have an existentially closed model of TG. Okay, right now in this theorem, I'm not assuming that the model companion exists. Okay, so it's a little bit more general. You don't need to check it. But say that you have existentially closed model with group action of group G, which is finitely generated, and M is stable. Okay. Then GMG, so the absolute Galois group, again, what was it? It was the automorphisms, right? And what is MG? MG is the fixed, all the invariants of the group action. So all the M's elements such that sigma G of M is equal to M for all G. Okay, so the absolute Galois group of the invariants G, that's ACL of MG over MG in language L, so in the language without group action. And I wrote this again, but yeah, I wanted just to explain it. So this thing is equal to the universal Fratini cover of the profinite completion of G. Okay, so you started with any group, you have this group action on X and an existentially closed model of it, okay? And then it turns out that the absolute Galois group of the invariants is actually determined by G, in the sense that it's the universal Fratini cover of its profinite completion. Universal Fratini cover is the smallest projective cover of this profinite completion G, and that's quite standard notion in the profinite groups. Okay, so one more thing: if G is also finite, then we have even something better, because we don't have just the absolute Galois group of the invariants, we have the absolute Galois group of the whole model, of the whole M. So in the case when G is finite, this absolute Galois group of the whole M is actually the kernel of the above Fratini cover. So making this short, we have if G is finitely generated, like I will combine right now these two things. So the PEC ingredient and group action in this conclusion. So if you have a G which is finitely generated and a model, existentially closed model of this theory of group action, then MG is unstable. I mean, it will be probably unstable, right? If G is not if G is not trivial, but it will be tame as tame as G. Why so? Oh, because from this theorem you have control over these two guys. Actually, okay, over this one maybe that's not so interesting, because if G is finite, then usually this MG will be simple, and we're trying to get examples outside of the class of simple theories. But even in the case of finite G, you have this absolute Galois group of the whole M, so that's more information. But even if it's not finite, then you have still information about the invariants. Okay, so GMG, absolute Galois group of invariants. And if it's existentially closed, right, then it's a PAC structure, and PAC structures are controlled by their absolute Galois groups. Okay, so here we see that how tame is MG, this M with group action, it will depend on the proper choice of G, because G controls absolute Galois group controls PAC structure. Okay, let us come back to the theory of fields. So now our goal is to start with a stable theory of fields and equip it with some non-trivial group action, and then determine the existentially closed models of this new being. So the standard examples are, if you have ACF, then you have AGFA. If you have DCF0, then you have DCFA, so differentially closed fields with one automorphism. If you have SCF, then you have separately closed fields with one automorphism. More precisely, if you have a theory of fields, then you have you make this first step, and then you have a theory of fields with group action of G, so this different setup, and you try to find the describe the existentially closed models, and there are exactly Gtcf if it exists. Okay, so provided that this guy exists. And why I didn't start it with ACF? Okay, I could try like here to ACF and then AGFA. At the end, I will have substructures of ACF, right? My fields with group action will be subfields of some fields with which is algebraically closed. But if you take a finite group, then existentially closed fields with group action of your finite group, they are not even separably closed. So you cannot simply take ACF and add group action of finite group. You need to take just fields, right, and add group action of group G, and then try to find existentially closed models of this existentially closed structures of this shape, right? So fields, group action, and then existential closed. And the same here. So if you have a theory of fields with M commuting derivations, then you equip theory of fields with the M commuting derivations with a group action by a group G, and this group acts by differential automorphism. And if you are able, you can find a model companion, so the theory of existentially closed such structures, and that I will try to do it today at the end. So GDCF0. So you have M, many commuting derivations, some finite group G, and G acts by differential automorphism. So the last analog is for separately closed fields. So you don't simply start with separately closed fields and add group action. You need to take theory of fields with P bases, and then equip it with group action, and then find the existentially closed fields with group action of fields with fixed P bases. But still, that's the procedure of breaking stability of a stable theory, right? Every time there is a stable theory in the background. Okay, so all these theories, maybe these ones, they are some part of the bigger stable theory. So structures are just substructures of some stable model, stable structure. Okay, I will tell you how to do the second dot. I mean, that's the goal for today. But let me start with a simple, say, baby case. So the Gtcf. That's just theory of fields, existentially closed fields with group action of a finite group G. Okay, that's how we started. We try to guess the axioms. We'll be at least, I think, convinced that these axioms work, and then we try to do the same axioms for Gtcf0. We look what's going wrong and then try to fix it. So axioms for Gtcf. We start with a finite group and say that G has E many elements, and a fit K with automorphisms, right? Again, I will use this convention where you have sigmas G. So it will be a structure, okay, that should be K. So K and sigmas, that's a model of Gtcf if this map, so take G and attach sigma G, you go to automorphism of K. It's a group homomorphism, so you have really a group action. That's just saying that you have a fit with group action. And then there is this next, the existential closeness, right? That's the axiom. So geometric existential closeness. Each difference variety has a solution in K, okay? And I just put it in quotient mark because it's not precise. So what I mean by that, it's exactly the property star, this axiom star. So for any P, which is an ideal, G invariant prime ideal, and F, which is just a polynomial outside of P, there is A, so a tuple in Kn satisfying this last condition, okay? So maybe I will reveal everything here and then make comments. Okay, so you start with a G invariant prime ideal P, and you would like to find element A, and also you have this F, but that's not important right now. You would like to find A, so a tuple, which will be exactly zeros of your P, of your ideal P. Because this ideal lives in x1 to xe, right? We need to have this kind of extension by many variables. So how many exactly, how many elements you have in your group G? Because this k x1 up to xe is equipped with induced group action. So what is this induced group action? You take sigma G on K, and then you permute x1 to xe, right? Because you have x1 to xe, so each of these guys, right, correspond to one element in your group G. In group G, you have e many elements, so actually you can list all elements of G from 1 to e, and then you have these corresponding variables, and then you can think about them like sigma J, so sigma H acting on. This is just sigma H times G. Okay, so you permute the variables and act by sigma J's on the coefficients of your polynomials. And that's the natural group action here. So you would like to find a solution, right? Zero of this zero of all for all these polynomials in ideal P, which okay, so A here, you need to, if you have an element A, you need to assign a tuple, so sigma J1 of A up to, right? So a tuple corresponding to this extra variables x1 to x e, right? That's exactly sigma bar on A. Okay, so for a G invariant prime ideal, which lives in this extended ring with induced group action, and there you take, there you check G invariantness, and there exists a tuple A in Kn, so a solution to all the zeros. So it's such that this sigma bar on A, if you evaluate it on, I mean, each polynomial from the speed will give you a zero, right? That's zeros. But you want to avoid being a zero of f. So this A, this tuple A, it's zeros for everybody from your G invariant prime ideal, but it's different from zero on f. Okay, and that's exactly also, I mean, okay, so to some extent it's quite similar. Okay, it's similar to all these geometric axiomatizations of many model companions of fields with operators. As the Schmidt derivation, that's all, I mean, almost the same. You need to, in a proper way, extend your structure. So here we have a different structure of finite group, action of finite group. So that's easy. You just take more variables, like x1 to xe, and permute them. And for Hasselschmidt, you need to use something like prolongation. Okay, questions? If not, let me continue. Also, okay, maybe that's not so important. There is one more detail here. So actually, all these x's they have this kind of dimension n, right? So it's more variables, but still it's finitely many. So the important thing here is that's the ring here. It has finitely many algebraic indeterminates. So let me make a comment on that and use it, because you can always try to write down such a statement, right? But you, in model theory, you need to write it as a first order sentence. Okay, and now I will make a comment why this particular axiom scheme star is a first order. So to make it first order, how do you do it? So if you have a G-invariant prime ideal, it will be finitely generated, right? So there will be finitely many polynomials, and these polynomials will have finite number of coefficients. So actually, this statement star is about some particular configurations of configuration of coefficients of generators of my ideal P, and also about coefficients of F. And how can I write in a one sentence that coefficients of the generators of P and coefficients of F are exactly as in this statement star? So that the polynomials which will come from my coefficients will give me a G-invariant prime ideal. Okay, so there are two things you need to check. You need to check that this ideal is prime, and that after moving by sigma, so permuting the coefficients at the variables and acting sigma j's on coefficients, right? So that you can code this in some way. That will be G-invariant. So G-invariant means that after action by sigma j, you get again the same ideal P, right? So there are two things you need to check. And to do it, we just use some result, which is really nice one from '84 by Van den Dries and Schmidt. And it says that there is a bound to check that a polynomial finitely generated polynomial in finite number of variables is prime. There is a bound on the degree of polynomials you need to check. Say that you have, this f times g belongs to p, then f belongs to p, g belongs to, or g belongs to p. So usually you need to go and run over all polynomials f and g, and by the result here I'm mentioning, by the result which is mentioned here, there is a bound. There's a bound on the degrees of f and g in the definition of a prime ideal. And also there is a bound on the degree of if some polynomial belongs to your ideal, right, and the ideal is finitely generated, it means that there exists, say h belongs to your ideal generated by f1 to fk. So it means that there exists h1 to hk. Maybe I will just write this. So say that you want to check that G belongs to ideal I generated by F1 up to Fk. So that means that G can be written down as combination of such polynomials H, K, Fk. Okay, and the paper by Van den Dries and Schmidt gives you also bounds on the degrees of H1 up to Hk. However, the important thing on the input is that this ring has finite number of algebraic indeterminates. And now let us go to and try to do the same with the axioms for Gtcf 0. So we start with naming derivations. We have m derivations. Then we have this language of rings extended by our derivations, a finite group. And we extend language of rings by derivations, and then also by the sigma j's for my elements of group. Okay, so I will start with k delta g. So that's my potential. That's a field with m commuting derivations and group action of g. And I would like to make it existentially closed. Okay, I would like to axiomatize existential closeness. So my first dot just says that it's a differential field with m commuting derivations. So I'm just saying that the first k and delta is as I expect. And in the second dot, I'm saying, okay, G is a group, G gives me a group action, but note it's with respect to the language with derivations, so there are differential automorphisms, right? So G acts by differential automorphism. And then the last dot is again the same as previously, so each difference differential, now difference differential, right? Variety has a k solution. So what does it mean? Again, let us be more precise. So now I have condition 2 stars. So if I have a P which is G invariant prime differential ideal, that's the new part, and F is any polynomial outside of this ring. Okay, it's a fancy ring. I will tell it about it in a moment. Then there exists again a solution, but now a solution with this variety. So it says this sigma a is 0 of P, right? Just vanishes every element from my ideal, every polynomial from my ideal vanishes on A, but F doesn't vanish on A. It's not 0. Okay, so there are some problems with it, and let me make a comment on that. So I think that I should explain what is this K bracket X and what. So, okay, so the first problem which we face is whether this statement is a first order statement. Okay, because I'll accept that everything looks fine. Okay, that's a perfect axiomatization of fields with m commuting derivations, group action of G, which are existentially closed. And actually that will be the final answer, but almost. We need to understand in what sense this condition double star is a first order. It can be written in a first order state as a first order statement. So our first try will be, why not again Van den Dries and Schmidt, right? Okay, we cannot use it anymore because if you look at this ring of formal differential polynomials, so you have k on x, right? And x is just a tuple of x1 to xn. Then you define k with this brackets x as just the formal derivations of xi. So in this way, right? Just take xi, some variable, and then write the formal derivatives. And in a natural way, you just extend the derivations, the differential structure on this ring. But kx, because you are allowing psi, which has no bound, you have infinitely many algebraic variables, so you cannot use Van den Dries-Schmidt result. And there is other way to do it, so we need to use the characteristic sets. So right now I will just go and throw a bunch of definitions from the differential algebra, but I hope that it's not so, but I hope that you are familiar with them. So first of all, I need to define what is canonical orderly ranking. If I have my indeterminates, I'm saying that one of them is smaller, strictly smaller than another one, if this this thing holds. So the lexicographical order, the left tuple is smaller in the lexicographical order than the right tuple. Okay. Any questions up to now?
I think you're good.
So let us move on. So if I have this formal differential polynomial, then I would just define a few things. So leader of F is called or denoted by UF, is the highest ranking algebraic interdeterminate in F with respect to this canonical, with respect to this ordering here, okay? Then the degree of F denoted by df is just the degree of UF in F. Rank of F will be the pair UF df, and again, ranks are ordered by a lexicographical order. And then I have separand of F. So that's a formal partial derivative of F with respect to UF. So in my F, there is this leader, right? And it's a guy of this shape, some algebraic interdeterminate. And then I will just do the standard derivation with partial derivative with respect to this UF. And that will be separand. And initial of F, IF, that's the leading coefficient of F when we view it as a polynomial in UF, right? So again, we just have some ordering on my algebraic indeterminates, and with respect to this ordering, I'm defining this stuff, which I think are standard. Okay, so more definitions. Sorry for that, but I need a lot of notions to write down the to translate this statement double star in a proper way. So if I have a finite subset of formal differential polynomials, then I will just define H lambda, right? If lambda is such a set, as just the the product of all the initials and separands of my F's from lambda. Then if I have any subset of these polynomials, by A with a rounded bracket, I denote the ideal generated by A, and by the square bracket, I denote the differential ideal. Okay, so that's the difference. I mean, that's the difference, right? So rounded is just algebraic thing, and bracket is also with the derivatives. And then the last part. So if I have ideal, this just ideal in my differential ring. Okay, so ideal consisted of differential polynomials, not necessarily a differential ideal, not necessarily closed under the derivations. Then I define this, I don't remember it, I think it's called quotient. Okay, I define this guy. And then I can say what does it mean to be reduced. So if I have two formal differential polynomials G and F is not in K, we say that G is reduced with respect to F if no proper derivative of UF appears in G. So my leader from leader from F, and its proper derivative. So you just take this this guy and try to add. You consider this kind of stuff, and this kind of stuff doesn't appear in G. Okay, with some powers here, and also other combinations, right? You can have delta G, so on. And degree of UF in G is strictly smaller than df. So the degree of UF in G is strictly smaller than the degree of UF in F. That's what the second dot says. And you have a subset of this formal differential polynomials, it's called it's auto-reduced if for any two distinct elements, right, one is reduced with respect to the other. Okay, so let me move on. And what is important here, auto-reduced sets are finite. So sometimes a prime differential ideal P might not be finitely generated, but auto-reduced sets which are contained in P are finite. So that's a perfect surrogate for, for finite generator. I mean, we need to check a few more things and then we can state the final axiom. So a characteristic set of a prime differential ideal is a minimal auto-reduced set contained in P. I will skip it. I will not say what is the ordering of auto-reduced sets, but there is also like this canonical orderly ranking. Similar thing is going on for auto-reduced sets. You can compare which you just order in some way the auto-reduced sets and you choose the minimal one of them which is contained in P, and that's characteristic set. So if you have a characteristic set, then the prime differential ideal P is equal to quotient. However, here we are not so satisfied. Okay, why? Because here it's still a differential ideal generated by lambda. Okay, I would like to have pure algebraic situation. If you have derivations, then you have infinitely many algebraic interdeterminates. Okay, so here Rosenfeld's lemma helps us. The following are equivalent. So lambda is a characteristic set of a prime differential ideal, and then it will be equal by the previous thing to this quotient, right? If and only if lambda is coherent and the ideal, and now we have algebraic ideal, right? So without derivations, is prime and doesn't contain non-zero elements that are reduced with respect to elements from lambda. Okay, I will not tell you what is coherent, but it can be also written down as a first order statement. So the whole story is that you cannot work with just generators of your ideal. You replace it with auto-reduced sets. And then you know that your ideal P is actually, it can be in this way generated from lambda, but from in the differential way generated from lambda. And then you use Rosenfeld lemma to replace this differential ideal with an algebraic ideal. So there is no more derivations here. And okay, there are some in some way, but I mean, not so. They don't show and they don't produce infinitely many indeterminates. And so we can replace this double star with the following axiom scheme. So for any characteristic set lambda of a G invariant prime differential ideal, right? So that was the thing which was making all the troubles or the problems. And any non-zero f. Okay, now I'm saying that f is reduced with respect to lambda, right? Why? Because I want to speak about this G invariant prime differential ideal P, but instead of, but I will just use lambda to characterize this ideal, to write everything about P in the terms using lambda, so h1 to hk. So f belongs to P. I mean, f doesn't belong to P if f is reduced with respect to lambda. That's exactly that f doesn't belong to P. There is a such that, okay? And the first part is that generators of P, they vanish on my A. And the second part is that actually, okay, so f is not 0 on this double A, but here I have also this h lambda, and that comes out from the lemma here, right? If I remember correctly. Okay, so let me just come for a second back here, where I was. Right, so we have this double star condition, right? If we keep these axioms here and only replace the last double star condition with the last one, this 3-star condition, then we got the axioms for our theory Gtcf 0m. So fields of characteristic 0 with m commuting derivations with group action of finite group G. And that's it. So, excuse me, thank you for your attention. And now I'm listening to your questions. I hope that I didn't extend too much, or did I?
That's fine. So let us thank Daniel for his talk. So do we have any questions for Daniel? So I have few. So first question is, so you mentioned, well, it's not a question, it's just to confirm, Gtcf 0 is simple, you said. That's correct.
Yes, that's true. That's true. So in general, if you have a finite group and you do this procedure I described in this talk, you should end with a simple theorem. And I mean, I can, you know, I can risk and say that it's all the time.
Right. And I would think, just like ACFA, you don't have quantifier elimination. Is that correct?
Right. And okay, so in all these theories, I think you don't, right? But in all these theories, you have the same, you have at least this quantifier elimination in the style of AGFA,
right.
Okay?
Right.
The semi-QE. But you have elimination of imaginaries
Right. Mm-hmm.
in this Gtcf 0m after naming something, some constants.
Okay. So maybe I'll see if anyone has another question before I ask one more. Any questions?
Yeah, maybe I can ask a question.
Right.
So from the perspective of difference algebra, maybe the most important or most natural example of a group to look at is C to the n, so finitely generated free abelian groups. Can you say anything about that case? So I believe there is no model companion in that case, but maybe some people looked at it. I mean, maybe still model theory can say something interesting about that case.
So you mean, for example, if I take Z and Z, right?
Yeah, C cross C.
C cross C. Yeah. So the model companion, as you know, as you guess, doesn't exist. I mean, it's well known for just fields without derivations, but here you also, I mean, the same argument holds. I mean, survives. You can just show using Krzyzewski argument that Gtcf 0 for Z times Z doesn't exist. Okay. But what can we say about that? So I think that it might be Nsop 1. Okay, that's some kind of guess here. And why so? There are results saying that if you have Kim independence on the level of the absolute Galois group, it will just go down to your field if it's PAC, and that's the case, right? You have PAC stuff here. So even if you have derivations, and I think that in the case when you have Z times Z, the absolute Galois group shouldn't be too complicated, okay? So it should have some kind of Kim independence there, and then you can drop it down and you get an Nsop, okay? That's my prediction.
Okay, thanks.
So do you mean any existentially close model will be an Nsop 1? I mean, this is
no. That was the question was for Z times Z,
yeah,
right?
Yeah, exactly. So you don't have model companions. So when you say you predict an Nsop 1, what specifically do you refer to? So
I predict. Okay, so I think that every existentially closed field with action of Z times Z should, or maybe not should, but that's my guess. It will be Nsop 1.
And do you know if this is like somehow close to be achieved for just existential theory, or is it any easier for existential theory?
What do you mean by existential theory?
Well, I mean, you can look at, in terms of positive logic at this rate.
Oh, I see. Okay. So I think that the main part here is this one of the theorems which I gave you, where okay, maybe I will share my screen again for a second. And that was a little bit earlier. Okay, here, right? So I'm not assuming that MG is existentially closed. I'm not assuming that the model companion exists. I'm just assuming that existentially closed model, that MG is existentially closed model of this DG, right? And then I have this connection between absolute Galois groups and group G. So if G is nice and Z times Z is quite nice, then the absolute Galois group should be also in some sense nice, right? It's the universal fraternity cover of Z times of the profinite computation of Z times Z. I'm not sure what is it. I don't know what is it, but it shouldn't be too hard, too complicated or wild. And then using all this co-logic in the absolute Galois group, you should be able to see that that's the Kim independence goes down in a nice way.
Thanks.
But that will be an Nsop1 in the pure field language, right?
Why? Is it obvious? It will be.
No, I'm not saying it's obvious. I'm just saying that I'm not saying, okay, I'm making it more precise, right? It will not be an Nsop1 in the language with in the difference structure. Okay, just pure field structure will be an Nsop.
Okay.
I cannot hear you.
Do we have any other question? So
yes, I'm sorry. Could he? My internet connection got lost. I wanted to see just the last 6 slides of his. If you could just scroll through those.
John, if you look in the chat, you will see the link.
Oh, he does have the link. Okay.
Right. There's the link for the slides. Yeah.
Actually, that's my chat. Well,
okay.
It got broken, so
okay, I'll put it back for.
Thanks.
All right. There you go.
Thank you.
You're welcome. Anyone? Any other question? So maybe let me ask. Have you tried any more geometric stability analysis, like for example, Zimba principle, or not yet?
No, not yet. Yeah, right now I will try. Actually, what I'm trying to do. I'm trying to understand, what to add to get how to break the stability in this, controlled manner. So, okay. I mean, the picture becomes clearer and clearer, and I think that at some point, yes, I would like to go to this deeper analysis of exactly more geometric stuff.
Right.
So, but that's not easy, If you look at the ACFA paper, the first one. Is
right. Thank you. Okay, so if we don't have any other questions, let us thank Daniel again. And so we'll see each other, all of you, hopefully on next Friday for Charlotte's Arduino talk.
Thank you. And I don't know, good afternoon. Afternoon you should have, obviously.
Yeah, it's afternoon here. Yeah.
I wish you good afternoon. Friday, we have Friday evening, so I would just rest.
Good.
Bye.